Okay, one more very important fact about polynomial functions and what their zeros can be. For a polynomial with all real coefficients, the zeros occur in conjugate pairs. That is, if the complex number a plus bi is a zero, then a minus bi must also be a zero of the same multiplicity. So that tells you that anytime you have complex number zeros, like if you had 8 plus 5i as the zero to a polynomial where all the coefficients were real numbers, so it didn't look like I was involved. But if one of the zeros was 8 plus 5i, then 8 minus 5i would also have to be a zero. That kind of makes sense if you think about the quadratic formula and how if it gives you something involving I, the I comes after the plus or minus. So you have something plus or minus something else times I. And a corollary to this theorem, and in math, a corollary is something that's true because something else is true. So because this conjugate pairs theorem is true, it must be true that if the degree is odd, you have to have at least one of the zeros that's a real number. If the degree is even, then it's possible that all of the zeros are paired up as complex numbers involving I. But if the degree is odd, if you have a degree 3 or degree 5 or degree 7 polynomial, you can't pair up the zeros that involve I. There's going to be one left out that doesn't involve I, at least. So let's look at this rule in action. Find a polynomial with all real coefficients for which -4 and 2 minus 5i are zeros. Okay, first of all, if we want -4 to be a zero, x plus 4, that is x minus -4, has to be a factor. And if we want the complex number 2 minus I or 2 minus 5i to be a zero, well, first of all, x minus that number, 2 minus 5i, has to be a factor. But from what we were just talking about, if 2 minus 5i is going to be a zero, then the conjugate 2 plus 5i, same real part, and then a different sign in front of the imaginary part, that also has to be a zero. So you've also got a factor of x minus 2 plus 5i. So this is what the polynomial would look like in factored form. Now let's see what happens if we multiply that out. And I'm going to start by multiplying together those last two factors that involve the complex numbers. So if I FOIL this, if I multiply it by the FOIL method, first we've got x times x, x squared. Outside we've got x times a minus 2 plus 5i, so minus 2 plus 5i x. Inside we've got minus 2 minus 5i x. And last we've got a minus times a minus would be plus 2 minus 5i times 2 plus 5i. Now let's do some multiplying out here. We got x squared minus 2x minus 5ix minus 2x plus 5ix. And then foiling here gives us 2 times 2 is 4. On the outside, we got plus 10i. On the inside, we got minus 10i. And last, we got minus 25i squared. And remember what happens anytime you get I squared? Right, that's really equivalent to -1. So now we've got this big ugly mess, but it can be simplified because look at some of the things that we have going on here. We have a minus 5ix and a plus 5ix. Those are just going to add up to 0. They'll cancel each other. We have a 10i minus 10i. That cancels. Let's see what's left. We got x squared minus 2x, so minus 4x. And then here's a plus 4, and then minus a minus or plus 25 gives us a plus 29. So when all the dust clears and we've done all the multiplying and combining, there's no i's left. The i's canceled, and we just have nice real number coefficients here. And now let's finish multiplying together the x plus 4 times the x squared minus 4x plus 29. X times x squared is x cubed, x times minus 4x is minus 4x squared, x times 29 is 29x, 4 times x squared is 4x squared, 4 times minus 4x is minus 16x, 4 times 29 is 116. Combine like terms, and that simplifies to x cubed plus 13x plus 116. So there we have a polynomial with all real coefficients, no i's in the coefficients, and negative 4 is a zero of this polynomial, and so is 2 minus 5i. If you took 2 minus 5i to the third power, plus 13 times 2 minus 5i, plus 116, it should come out to equal 0. Next example, find all zeros of this polynomial here, f of x equals x cubed minus 13x squared plus 55x minus 91, given that 3 plus 2i is a 0. So we're told that 3 plus 2i is one of the zeros of this polynomial. And there's 3 zeros in all because the degree is 3. So this degree 3 polynomial has 3 zeros, and we already know one of them because that's a freebie, 3 plus 2i. And if 3 plus 2i is a 0, what else has to be a 0? 3 minus 2i, the conjugate. And that leaves one more 0 that we still have to find before we'll know all 3 of them. From Descartes' rule of signs, let's count the sign changes. Positive to negative, whoops. Positive to negative, negative to positive, positive to negative, 3 sign changes. So the number of positive real zeros is either 3 or 1. It's the number of sign changes, or it's that number minus an even number. It always goes down by 2. Well, all 3 of them can't be positive because we've already found 2 of them and they're not real numbers at all. But the one that we haven't found, that must be a positive real number. So that third 0 that we haven't found yet, we can at least say that it is a positive real number. And it has to be a factor of 91 over 1 if it's a rational number. So let's start trying numbers that fit that description. If we try 1, set up the synthetic division, bring down 1, 1 times 1 is 1, negative 13 plus 1 is negative 12, 1 times negative 12 is negative 12, 55 plus negative 12 is 43, 1 times 43 is 43, negative 91 plus 43 is not 0. So, sorry, 1 is not a 0. What else can we try? Well, what other numbers are factors of 91? It's not divisible by 2. It's not divisible by 3 or 4 or 5 or 6. Is it divisible by 7? Let's see, 91 divided by 7 is 13, yes. So 7 is a factor, and if that doesn't work, 13 could be a factor. But let's try 7. Bring down the 1, 7 times 1 is 7. Negative 13 plus 7 is negative 6. 7 times negative 6 is negative 42. 55 plus negative 42 is 13. 7 times 13 is 91. Negative 91 plus 91 is 0. That worked. So that third 0 is 7. Now we know the zeros. 3 plus 2i, 3 minus 2i, and 7. And since we know them all, we could stop right now, but I want to point something out. When we did the synthetic division and found that 0 was a 0, or 7 was a 0, we also got a quotient of 1x squared minus 6x plus 13. So we know our polynomial factors into x minus 7 times x squared minus 6x plus 13. So the zeros of that polynomial, well, one of the zeros is 7, and the other two zeros are the numbers that make x squared minus 6x plus 13 come out to equal 0. If we didn't already know what those were, we could figure that out by solving that quadratic equation, by using the quadratic formula or completing the square. And if we did that, and in fact, we did that right at the beginning of this series of videos, if we use the quadratic formula to solve that quadratic equation, turns out that the solutions are 3 plus 2i and 3 minus 2i. So even if we hadn't been given the 3 plus 2i as a starting point, if we found that 7, we could factor out that x minus 7 and then worry about when is x squared minus 6x plus 13 equal to 0. And once we figured out when that is, we'd have all three of our zeros.